So, as the last block for today, I would like to talk about frontends. We won't finish this chapter, so just the first block of this course on SLAM frontend. So far, the focus of the course was mainly on the different SLAM backends, or the ways on how do we tackle the state estimation problem in the sense of how to minimize the error, how to estimate the probability distribution about the configuration of variables. And so far, we basically always assumed the data association was given. It wasn't necessarily assumed that it is always perfect, but at least it was assumed that it is given, so that we know about the data associations. And what I would like to look into today a little bit, at least on an abstract level, on how to actually generate those constraints. The problem is it strongly depends on the sensor that you're using, how good your constraints are and how you compute the constraints. But at least I provided that for laser-based system and an idea how we could actually do that division, and then in the end present an approach, which is probably something which will happen in the first hour of next week, on how to make decisions which constraints are actually consistent, or how to identify inconsistent constraints to not add too many false positives to my optimization framework. So we had this idea of graph-based SLAM. We have the robot that moves through the environment, and whenever the robot observes the same part of the environment, we can actually generate those constraints. We are today interested in actually finding those constraints. So how to get the errors. And I also told you once ago that you typically have this interplay between front end and back end, so that we have the front end which takes the raw sensor data as the input, and therefore this depends on the really raw sensor information. So for every sensor that you're using, for every camera, for every different type of laser scanner, you actually need to implement a new front end. Of course, you can potentially reuse parts, but it strongly depends on the quality of the sensor, how you actually implement your front end, or how you actually keep the tuning parameters. So it's strongly sensor dependent and not that nicely decoupled from from the raw input data compared to the back end, the optimization approach. And so today, we're looking here to the front end part of that. And so one way for actually obtaining those constraints is from matching observations. So we briefly did or introduced the scan matching on a very, very short basis, and which tells me how do I relate, for example, two laser scans. And I can actually do this with, let's say, raw laser data. I can take the raw laser scan, another raw laser scan, taking at nearby locations. I can overlay them so that the endpoints end up in the same locations, and in this way compute my relative transformation. Sorry. So this is what we call dense scan matching. The other thing I can do is I can actually do a feature-based matching. So if I have, for example, the trunks of the trees in this example is typical Victoria Park data set scenario. You see trunks of trees and you say, there's a distinct feature, there's a distinct feature of a tree, then just match the trees with each other. I can do the matching based on nearest neighbor approach or like global assignment techniques. There's one way I do the matching based on landmarks. And the third group of approaches typically does constraint matching based on descriptors or feature descriptors. So for those of you who attended the computer vision course of Thomas Brock's, may have seen SIFT features or SURF features or some ways for features that I can extract from images. You can see that as for a certain point in the image, these descriptors analyze the local neighborhood and generate a descriptor for that local neighborhood. It's a vector which tells you, which typically depends on the gradients you have in your image, to be a little bit at least independent from lighting conditions. And so there are a million ways of how to compute feature descriptors, but the popular one analyzes the local structure and uses the gradients, and then matches the, for example, images based on SIFT features that you have. So you get correspondences between this pixel, should be the same pixel in this pixel. If you have that for multiple pixels, depending on how you start, you can actually reconstruct the local geometry. So these are different ways in how one can do that. We'll just briefly talk a little bit here about the different ways, or how this is realized in different systems. One thing is, in the kind of the naive approach, we take local observation, a local scan, and we would have to match this against all previously recorded scans or observations. The problem is that's an operation which is very costly. First matching typically is not always fast. Sometimes you can optimize it, it's fast, but not always. And what you typically want to avoid is try to match your current observation against all previous observations. And one way to avoid, there is a way to avoid matching a goal against all previous observations. Build up your graph in the context of graph-based, in the context of graph-based SLAM. You have already built a huge graph which has millions of nodes. You get new observation, and you don't want to match against all of them. What's a good way to do that?
Well, we could use the nearest neighbor. So let's say, I mean, obviously, if you're not near loop closure, then we just use the last few. That's the easy thing. But if you're close to a loop closure,
which we don't know.
Which we don't know. But here's the thing: we could just use the radius and say, okay, every node that lies within the radius of the current node or the previous node of some value, we match it against those.
Yeah, so if you replace the radius by the uncertainty about the node and then some sensor radius, then you're actually there. So what we need to do there is we take into account the positional uncertainty of all the other nodes in the graph relative to the current node I have, and see which one actually overlap with the current node. That's actually one efficient way to do that. So if this is the current position of the robot, and that's the kind of the sensing range that you typically have, for example, from a laser scanner, just takes the maximum range reading, gives you this blue circle over here, and then you traverse your graph. So you have two nodes, B1, B2, two should be actually out here as well. And then you can say, what is the uncertainty of this node B relative to A? And this is something we know how to compute based on the H matrix. But then you can compute the uncertainty of this node B. You need to expand it with the sensing range, and then you need to check if these circles overlap. So here these two circles overlap. So it may be that A and B are in the same area, in the same place, but A and B are very, very unlikely to be in the same place. Of course, if you have Gaussian distributions, there's always a non-zero probability that actually A matches to B2. It may be possible, but the probability is very, very, very small.
But okay, so around B, the dashed line is the positional uncertainty, right?
So yeah, so this is a sensing range of B locally. Sure. This is positional uncertainty, and this is kind of the uncertainty expanded by the result. This one added here. Okay. So this is the uncertainty. The dashed line is the uncertainty of B with respect to A, and then you need to add the sampling range, because it may be that B is standing exactly out here, so observe this area.
On the horizontal axis, though, that doesn't seem to.
Sorry, on the
horizontal axis.
On this axis, maybe that this is a scaling error of generating those pictures because I haven't drawn it. So maybe that I've scaled that suitably, or while converting it from the different PowerPoint slide. So that this thing should actually be here. So it should be probably a bit bigger. So see this as a drawing error on the slide. Now the key thing is there's no overlap between B2 and A. And if you, let's say, take into account 3 sigma bounds or 2 sigma bounds, you can say it's 95 or 99% probability you're outside. You may miss a potential correspondence with a certain probability.
Do you always estimate these or distances for all the nodes, or do you have some kind of optimized data structure where you already own them?
So what you can do is the problem is if you want to exactly compute. So typically you have to do this for all nodes, but you can actually update that when you will. Under this, so a previously computed solution can be reused at least in an approximate way to some degree. What you typically don't have to do, you don't have to invert this whole H matrix all the time. There are approximations that you don't really need to do the matrix inversion, which is something which is called a Dijkstra expansion, where you have the graph and you just propagate the uncertainty through the graph without considering the loop closures. That means you get uncertainty estimates which are bigger than those they are in reality. So you need to check too many nodes, but at least you don't miss one. So these are ways you can actually optimize this, because this is often cheaper than doing the matrix inversions. And you can also update this belief typically by, if you're in the center of the uncertainty, so the uncertainty is computed relative to a certain node. With our other nodes, you move a little bit further, you know your relative uncertainty of this node, so you can expand all the uncertainty levels a little bit. So you can actually have at least approximate ways for updating this uncertainty estimates of the other nodes. Any questions? Any further questions at the point? Okay, so what we actually have is these views may overlap, so you may can match A and B, but those it's very likely that they can overlap, and you typically discard them. And one way for actually computing those matches, at least if you work with range data, is to use something which is known as ICP, or iterative closest point. This is one way of performing scan matching. What you typically have to do for that, you need an initial guess. You say, I record a scan here and I record another scan here, and they're likely to overlap. And then you compute, do actually kind of error minimization on minimizing the distance of the endpoints of your laser scan. You still need to do the data association to typically iterate that. You optimize a little bit, you do your data association, you optimize, and so on. This works quite well if you have a good initial guess, but it's very likely to fail if you have a bad initial guess. That's one of the problems of these ICP-based methods, and what you can do is you simply introduce the threshold in a very ad hoc way, introduce a threshold. If 90% of the scans overlap nicely, I may accept that, otherwise I'm going to discard that. That's one way to do that. Yeah, so as I said, one of the problems is actually, as I said, I'm sensitive to the initial guess. Can you imagine any other problems that may come up from such a procedure? Why such a procedure could fail? So take the current scan I have, and I match it against a subset of other and I know which local areas are in the uncertainty loops. I want to match against them. How should I do that? Let's describe the approach, and then it's easier to identify the errors.
Using this nearest neighborhood in the ICP we just discussed here.
Sorry, could you repeat that, please?
The ICP basis the nearest neighborhood point-to-point differences.
Yeah.
But I'm not sure whether you want to use this point-to-point or point-to-plane, but I think
that actually doesn't matter much. There's kind of different variants how to implement the ICP approach, but it's still the important thing is it's sensitive to the initial guess. Depending on where you start, you may come up with a good match or a bad match. That's one of the real big problems you have with these kind of approaches. But there are two other approaches to be matching. But even if they match perfectly, the perfect overlap of the scans, what could still be an issue?
What do you mean by perfect overlap?
So let's say you have a current observation that you observed right now, and one which you've seen at a different point in time before, they perfectly overlap, so they perfectly match with each other. Is this a match? Is this something you can commit on?
Can be like two different parts.
the same area.
Exactly, you can have ambiguities in the environment. So if you have two rooms in the environment which look exactly the same, the robot has seen only one room so far, then enters the other room and says, oh, perfectly, this is the room where I've been before, it looks identical to the room where I've been 10 time steps before. If the robot doesn't know that all rooms in that building look identical, you're very likely to fail. So ambiguities in the environment is also one of the big problems you have with these types of approaches. What else could be problematic in here? Or not problematic, but at least costly?
Time computation because we have to
Sorry?
Time computation because we have to apply this for all the observations we have of the landmarks and the environment, and then uptaking the whole graph here.
So consider even the exam. I mean, of course, the more potential places you have to match against, the more expensive it is. I completely agree with that. Consider the thing you have only, let's say, 3 or 4 places in the environment where you could be. Say 3 or 4. I'm either in this room, or next room, or the next room after the next room. And you have an observation. You say it could be here, there, or there. What is still problematic with this ICP-based approach? Given that it is sensitive to the initial guess.
So I mean, you could end up using finding local minima?
Yes, so that's a problem that is sensitive to local minima.
So correctly, you have 3 possible rooms. So you have 3 matches, scans that you need to match your current match against?
Yeah, exactly.
So you try each one,
Yeah.
and on each you get an error number,
Yeah.
and you pick the one with the highest, the lowest score.
Yeah. Yeah. So you're close to that. So one of the problems, of course, of the threshold, how to determine this threshold. It's clearly a problematic thing for some provided a tune. But the other issue is that just by knowing I could be in this room or the other room or the next room, you still typically need a lot of possible starting locations from which you start your ICP to make sure you end up with a good match. Even if you're in the same room, you may need to sample a lot of locations from which you start your ICP to come up with the correct match, to not end up in that local minima. So it's kind of a problem which is coupled that ICP is sensitive to the initial guess, and sampling locations from which you start the ICP can be pretty inefficient. And you still have the problem with the ambiguity of the environment. So I will start with telling you examples of how you can actually address these two problems. And then the ambiguities in the environment is something which we probably do next week, because there's not enough time for today. But we at least look into these two aspects. ICP is sensitive to the initial guess. There's a few examples on how you can actually address this problem. These are all systems which we built here in Freiburg. So this was one of the auto platform which has a laser range scanner on a pen tilt unit, so it can actually pen and tilt the laser scanner, and in this way compute 3D maps from 3D point clouds. So this is one of the examples. So this is a building that we are sitting in. Red is non-traversable, yellow is traversable. You see things get untraversable here. This is the grass area on the side of our building. Depending on how high the grass is, the road may identify this as an obstacle or not. There's another example. This is the Stanford Car Junior used in the Urban Challenge, and we had a collaboration. We used the data here on the car from the 3D scanner to build actually a model of a parking lot that actually you can then do autonomous parking. That took the work of Rainer, who then did autonomous parking with that car within the parking garage. Another example is one of our blimp platforms, which has a camera. So it's the blimp. There's a small camera. You're looking downwards, observing the ground, and you can extract features, observe features from the ground it's observing, and then match those features against each other in order to do the data association. These are a few examples I would like to just introduce you how you can actually do that. The problem is that building a front end is very, very sensor dependent, so there's no gold standard, and you have to do it exactly in that way. It simply depends on the sensor platform you have, on the data you get, on the accuracy of the data, if an approach lasts you to work, or it may fail. So it's pretty sensor dependent, and therefore in this course I focus much more on the back end than on the front ends. Because whenever you get a new sensor, you may need to revise your front end completely, depending on. I mean, of course, some aspects you can reuse, but how sensors actually matched against each other, observations, strongly depends on the quality and type of sensor that you're using. Please.
Are we also going to talk about mobile landmarks?
Sorry?
Are we also going to learn about how to deal with mobile landmarks?
So with dynamic changes in the environment, I'm not going to cover that here. The reason for that is there are a few approaches which have been presented on how to deal with dynamics, but there's no gold standard yet. So there's no solution on how to do that. So I may illustrate this. In the last course I also wanted to talk, as it was kind of asked here, about open issues, or what are things which haven't been solved yet in this context. And dynamic environments is definitely one thing. So there have been, for special situations, special solutions on how to deal with dynamic changes in the environment, either by having some background knowledge, by doing certain assumptions, what kind of dynamics is one experiencing in the environment, but there's no kind of gold standard solution here, and therefore I haven't presented this in the course here, but I will definitely talk about that next week. I will provide a few examples on how you can actually do that, or what are approaches that try to solve that, and what are their limitations. Any further questions so far? Okay. Okay, let's start with the first thing. You have this robot which takes this pen tilt scanner and builds a map of the environment. So it builds local maps using the pen tilt scanner, and then tries to match these local maps or local point clouds against each other and put that into an optimization framework. So it looks like this. So you have a robot. This travels with odometry. Then it takes a 3D range scan by having this So something called the yes laser. Nothing. No lasers. It also exists, but it's the yes laser. And then it takes its scans, and based on the odometry or local odometry or locally matching those scans, you actually get a small 3D map, a small local 3D map or 3D point cloud of yours. So then the robot again dives a little bit, takes the 3D scan, and generates another local map. You then can actually start matching those local maps under the assumption that you can build those maps kind of consistently. Accurate sensor, potentially a platform is standing while it takes those scans and doesn't move. Then you can actually align those scans quite well. Well, you then, by matching those maps, map I and map I plus 1, you get your 6 degree of freedom constraint. This is X, Y, V, your control, exactly the way we did that so far. And then you put that into an optimization form. Then you actually can compute your local model. Okay, so aligning scans. So this is a small animation which the blue scan is the first scan and the red scan is the second scan, and you want to match the red scan against the blue scan. In the beginning, you can see that the red scan is a little bit rotated to the left. And these are the individual steps of the alignment procedure. It aligns those two scans by simply minimizing the distances between those endpoints of the blue scan and of the red scan.
But these are points, right? And yeah, I mean, how you can't guarantee that, like if the laser hits one point and then the robot moves and then the laser obviously hits the same surface. How do you, because
you cannot, you're completely right, you cannot guarantee that. There are different ways to actually approach that. One thing is you say, in average, I'm off in every direction a little bit, so it cancels out. It actually works quite well. It's kind of density scan. If you have points that are far away, like in this area over here, it doesn't hold anymore. What you typically take into account is a discount for points which are very far away to actually account for the fact that the opening angle of the scanner generates points which are further away. We have a weighing function there. Other techniques you can do, what's often done, that you compute local normals and then kind of do a kind of plane matching in the local neighborhood to actually get rid of that effect. They actually, whatever, I don't know how many variants of ICP, which I said before, point to point to plane, point to line, line to line, plane to plane, normal to whatever. So there are different spirits of ICP and how to do the matching to optimize it again to specific situations, to specific sensor setups. But yeah, this is an issue. Data association in ICP is an issue, and that's also the issue why it is so sensitive to local minima. So you can even see when you have the starting point over here, where the red plane starts here, you could, let's see if I can pause the video. So this is not a video, this is an animated GIF, therefore I can't stop it. You can see if you start at the beginning over here, you could perfectly, the nearest neighbor assignment of that plane of the red, of this plane, the red plane, it could be anywhere on the blue wall over here. The further you away, the more likely you have mismatches. Therefore you typically iterate a little bit, redo the data association, iterate, redo data association, and so on, but you're not at all guaranteed to get the right data association. One way actually to address this and make this approach more robust is to add some background knowledge about what kind of structure you are actually observing. And one thing that you anyway typically do with a mobile robot is you estimate traversable areas in your local environment if you want to drive, non-traversable areas, and potentially other like vertical structure like walls you may need for your navigation task. And instead of doing the ICP where you just match point against point, you can actually split that up into endpoints which lie on vertical objects, endpoints which lie on traversable areas, endpoint which lies on non-traversable areas. And then do the error minimization, only matching non-traversable against non-traversable, traversable against traversable, vertical objects against vertical objects. Or you can actually, if you have a few distinct features, you can first match only the distinct features against each other, and then end up with a quite good initial guess, and then redo the optimization. Or you can use cameras that you have additionally on the sensor and do a matching based on color. If you register your camera with your laser scanner, you may use color to also get a better data association. So there are, as I said, millions of different ways on how to do ICP, how to robustify ICP, and how to, let's say, exploit most of the sensor information you have in order to come up with good guesses. But as I said, there's hundreds of different techniques. There's just one way on how one can actually do that. So then we can actually build up the model. So this is our building over here, and you can see here this corresponds to this sidewalk road was driving on the small path. So all the red area here corresponds to the grass which wasn't mowed that well. So all these obstacle areas over here, this obstacle area over here. But you also see is here. You see all these small lines over here. These are small alignment errors from the individual maps that you align with each other. Because you take your 3D scan, you align all of them, so you can actually see the sum of few of these lines actually here. So at least you can visually see which scans were used to actually explode them. Another example is here done in the with this cow. The cow is driving around this parking lot using the 3D scanners and the navigation system. It's also an accurate IMU to build also local 3D maps quite similar to the approach which was used before, and then match them against each other and come up with a rather accurate model of the environment. And that's how the parking garage looks in reality. So it's a picture from the parking garage and the corresponding 3D model signature. As you also see here, look inside the planes on the ground. And so this example, kind of 1,600 local maps were built with local maps were aligned and then used for planning. And that's actually an example of the work of Rainer. There's my cursor. Yeah. Where you can actually see the cars starting here, driving into the parking garage, autonomously localizing with the scans in the model which is previously built. This is kind of a special kind of data structure. It looks a little bit ugly, but it allows the vehicle actually to localize quite accurately. Using the laser scanner, which is here on top, observing the environment, can plan its path, and then drives up to the top floor and actually parks the car in there.
Is this real time?
I guess so. Yeah. So the steering wheel turns quite quickly. This is always something which most of the autonomous cars actually do, unless you specifically take care of that. Therefore, it looks a little bit, does very hard, brutal steering maneuvers. But yeah, that's it. The person sitting here just does it in case something happens. There's an emergency button to take over control. And now you see it. Car drives on top of the parking garage, and then it takes a while, but then also parks the car there. Another approach I would quickly show is these flying vehicles like this blimp, which has a camera which looks downwards, and typically you have also an IMU, which gives you a rough estimate. It's some approximation of odometry on where you move, with what this IMU typically give you as well is the gravity vector that you actually solved already 2 of your angular problems. The estimated gravity vector actually works quite accurately, and so you can actually exploit that for your mobile platforms. And so in this case, you can have either a stereo camera. Just typically these things have to be lightweight, so this is kind of 2 cheap webcams assembled and build a stereo setup out of that, or you even have only a single camera looking downwards. Again, this depends on the platform. And these are typically images you get from these cameras. And you see this one here. This was the carrying the camera over grass. You see that it's actually quite difficult to do, even for us as humans, to align this grass area against another grass area. So it works astonishingly well, but with features, descriptors, and also the arrangement, the spatial arrangement of those features, that you can actually exploit that and build models out of that. What the approach uses here is, again, one of those visual features, SURF features. This is a variant similar to SIF features, which can be computed in a more effective way, or more efficient way. And for some kind of points, I don't want to go to the details of how the points are selected and how the descriptors are computed, but for every of those dots over here, you have a descriptor which represents a local surrounding. You can actually have quite a lot of them, and this allows you, even if some of the associations are wrong, from a second image, match against the other image by saying, I have descriptors of the local surrounding, and I match the local surroundings against each other. So if you say, assume we have this down-looking camera, and we have a 6 degree of freedom problem, so for every position we have an X, Y, Z position of the camera and the yaw pitch roll. If we have that IMU, we should know what the gravity vector is, which is very nice because it eliminates 2 of these rotational constraints that we have. because the pitch and the roll, so this and this angle, actually get compensated by knowing what the gravity vector is, but the regular rotation and the 2D rotation you can't identify with that. Yeah.
Can't you use a compass?
You could use, but especially on these flying vehicles, you have motors which spin quickly. Compass is quite useless. I mean, you may have very expensive shielded compass, but they're typically much heavier than what these platforms can carry. So at least if you have these kind of small-scale platforms, compass can help, but depending on the properties of the platform, these estimates are typically not that good. At least if you don't spend a huge amount of money. So I mean, there are navigation systems in the order of 100,000 euro. They work quite well. Typically, they're much more heavy. They integrate INUs with different kinds of compasses in English. So different techniques. And different kind of techniques in order to also fuse the information, merge this with GPS information. There are different ways of doing it quite accurately. The problem is the devices are comparably heavy and quite expensive. And so if you use a simple, even these small INU, which was shown before, costs around 2,500 euro. You get the gravity vector quite accurately, but the compass there is, at least on these platforms, more or less useless. It's a hard statement, but at least it's not as, it's orders of magnitude less accurate than what you get from the estimated gravity vector. So what you then do, you have your, for example, down-looking camera. This is what you see in the current image. These are maybe features that you've built to your map. And just by matching those, the feature points that you see here, and the feature points that you see here, you can do the computer transformation and then the alignment that you say, you have an overlap here, and this image should actually be here in your map, and then generate the constraint out of that. So how do you do that typically? You typically have a lot of features, so you need an efficient way for querying features which are close in descriptor space. So we're not talking here about X, Y, D space, where the points are in space, but in the descriptor space, which is for SIFT-SURF either a 64 or 128 dimensional vector, and you want to have nearest neighbor queries which are done efficiently. The stupid way would be just store all of them in a list, and just pick every feature and compare the current feature descriptor against feature descriptor. You sort your list, you iterate over your whole list, it will be linear in the number of features you need to match against. You can do that in a smarter way using KD trees and KD tree data structures, so you can actually bring that down to a logarithmic number of comparisons you actually need to conduct, and you can do approximate KD trees, and in this way be even more effective in here, more efficient in here. What you typically use of how this approach works is kind of a Renthik-like procedure, and what you do in here is you select the best matches which fit, just let's say 2 in this case, or the number of feature matches you need to know depends on the exact degrees of freedom of your problem. If you know the role of the pitch angle, in this setup you only need kind of 2 correspondencies in images, then you can compute the transformation between 2 images and then see how well do all other matches actually fit. And then you kind of can sample 2 new features, match them, and see how well do all the others fit. This kind of iterative procedure which you can actually use to quite robustly align images until you found a transformation which minimizes or gives you very, very small reprojection error of the features.
Is this just the part 2, so just Renthik?
This is a Renthik, yeah, the way of doing Renthik, exactly.
But starting with the best. So
this is kind of ProSec or GoodSec, which are variants of Renthik, which typically are quite efficient if you have good guesses. So they're different. Renthik again has a huge variety of different variants. It's a GoodSec, ProSec, I think it would be GoodSec, I think, which was usually we start with the best matches and then continue with that. They're just variants depending on the way you use them. So Renthik you can use if you have no idea which of your constraints are actually good one and best ones. Here the feature descriptor gives you already an idea where you have close correspondencies in features in descriptor space and far away correspondencies. And those which perfectly are more likely to be correct ones. So it makes sense to start with the good ones. And that's kind of the way the approach does it here. But it's just a matter of typically of efficiency. So if you have more computational resources, you can do more iterations. Renthik will, in the end, lead you to the same, or potentially even a better result because it simply tests more hypotheses made from their research. Okay, so if we have that, we can actually align two images with each other, and the question is, how do we actually find the edges that we want to add to our graph? The one thing we typically do is visual odometry. So you match the current frame against the previous frame or the previous end frames, and in this way estimate an odometry from the downwards looking camera. That works quite well. If you already added edges, so you know where you are on your map, you can actually perform some kind of localization approach where you kind of estimate from the visual odometry which way you move, and then look very locally for correspondences. Or what you also have to do from time to time, look for loop closures if you have traversed through unknown areas and you need to measure against different parts of the environment. And that's actually the interesting part when most of the errors actually occur. A small video, so this was the first dummy setup. It was actually the master thesis of Basti, steht and all that. So he built kind of this kind of fishing rod style thing where the camera was hanging downwards and walking over the grass, and you can actually see. So this is what the camera sees, and these are the features which were mentioned. You can actually see he walks over large grass areas, and it works surprisingly well that you can actually estimate that he walks in a straight line. Of course, the angles are not always correct, but the result is not too bad. Tour one around our building.
Is this a stereo camera?
Yes, this is kind of self-made stereo setup, so you get a very rough estimate about the distance and about the size. So otherwise, the scale would be completely up to you.
And it has the odometry you described.
So it only uses it uses visual odometry. So basically, there's no odometer, there's no wheels that you could attach it. We only have the IMU to get the gravity vector, but it's only used for the gravity vector. Here you can see the first loop closing constraints coming up. There's a system identified loop closures, and then you can now localize this part in this map. And now you can actually do the graph optimization. And so this is actually the Tor, the gradient descent based method, which was used in here. You can see how it actually folds those maps together. This way it ends up with. And if you actually overlay that with that at that time quite bad Google Earth, you can actually see the rough trajectory that you walk. Did you know the environment? So this is our building. This is where people often make the barbecues, and this is the grass area. So it actually resembles the trajectory, not too bad. I guess we're running out of time, so I'm actually done with the first part, and we'll continue with the front ends in next week, and then especially look into ways, given that we have matches, how do we identify which matches are consistent with each other, where do we have inconsistent ones, and then actually come with a kind of rejection technique on which constraints to add, which constraints to remove. This is actually one of the state-of-the-art techniques which is used today, at least in all our mapping systems and most other mapping systems as well. Okay, thank you very much.